Greetings of the day. My name is Simrat Kaur and I am a student of class 11 Science, School of Eminence Samlo, District Fatehgarh Sahib. My project is titled Exploring Mathematical Behavior in Scientific Systems. This project comes under the theme of recreational mathematical modeling because it uses mathematics to explore and compare how different scientific systems behave, not to build a device or to solve a social problem, but to understand patterns, logic, and limits of prediction. My project shows that mathematics does not behave the same way in all systems. Sometimes it shows order, sometimes chaos, while sometimes it may show probability, but sometimes it shows exponential growth. But the basic idea which I want to convey is that mathematics is not only about formulas, it is about the behavioral change. My project's first model is domino, which is based on the cause and chain reaction, and it represents that one small action triggers many consequences, and it teaches us that every cause leads to an effect. It works in the sequential method, and the last one, which is amplification. It means that one small input results in drastically exponential output. This is not chaos, this is causality. This is the simplest form of the butterfly effect, which states that one small push deciding many outcomes. Now, we will look at the physical demonstration. Here I have 8 blocks in line. This small block, I will give an input by just touching. Now, here, this small block caused this big block, which is as 4 times larger than this one, to fall. Now, you may ask, where is its real life application? In 2003, a single tree branch touching a power line in Ohio caused a complete blackout of electricity in northeastern United States and parts of Canada. Mathematically, it's a network cascade, but it is also an example of domino effect, just like our wooden plates. The second model of my project is single pendulum, which is the epitome of order and predictability. All my models are interconnected with each other, they are not separate, they just show the different phases of mathematical scientific behavior. Now, single pendulum, which is a perfect epitome of order and predictability. Now, what it represents? A system that follows rules and remains predictable throughout the process. Now, what it teaches us? It teaches us regular motion, stability and repetition. The same laws produce the same result every time. This is the perfect example of mathematical order, the science or math which we learn in our textbooks. Here is the physical demonstration of single pendulum, which is the epitome of order and predictability. Now, I will give an initial input in the form of force to this pendulum. Now, look at this oscillating arm. This shows periodic motion. With same initial conditions, this is perfect periodic motion. Here, if we know the initial values, we can find the outcomes or its position using the formulas by putting the values in the formulas. This is the perfect physics that we learn in our textbooks. Now, where is the real life example? The real life example is a student who works regularly, learns regularly, practices consistently, and revises on regular intervals of time. It is predictable that he must perform good in his exams. We can predict the future easily. This is the example where the initial conditions are so obvious that we can easily predict the future outcomes. Now, the third model of my project is double pendulum, which shows chaos and sensitivity. It represents same laws but unpredictable behavior, and it teaches us sensitivity to initial conditions, non-linearity, deterministic chaos. Same laws, same gravity, one extra degree of freedom, and suddenly predictability collapses. Now, here is the physical demonstration of chaos and complexity. We have a double pendulum with us. I just added one more arm to the single pendulum. I didn't change the laws of physics, I didn't change gravity, just one single arm. Now we will see how chaos works. Deeply observe the angle which I am using. First of all, we will give the input with an angle of 90 degree. The arm swings. Now, we cannot predict the motion because motion is unpredictable due to the interchange of energy between the two arms. They cannot be predicted by using simple laws. They can be solved with differential equations, but there is not a closed answer to them. Now, we will input them with a different angle, a slightly different angle from the previous one. Now, look at the motion. This trajectory is completely different from the previous one. This is what we want to convey through this model, that complexity lives next door to simplicity. The important point to be noted here is that this motion is not random. This motion is deterministic, but it is the highest order of complexity. It is not random, it is complex. And this is what we call the art of double pendulum or the art of chaos. The fourth model of my project is probability board, which shows probability and divergence. It represents divergence of paths due to repeated small choices. It teaches us binary decisions, path dependence, and why outcomes scattered. Same ball, same drop, a cascade of tiny collisions, and a predictable path scatters into the unknown. This is the model, the probability board. This is not a Galton board, it is a probability board. It is my invention where I have arranged these pegs in a complex manner. They are arranged in a very complex order, and when we will throw a ball from here, at each peg the ball will have two choices, either to go left or to go right. When we will drop this ball, at each peg it will have two choices, either to go left or right. Now, this shows divergence, the divergence of paths, and here the idea emerges. Probability does not guarantee identical outcomes, it only defines likelihood. At each peg, the ball had two choices, either to go left or right. But the probability caused a completely different pattern. Each ball went into different slots, even though the path was predictable, but still the outcomes were scattered. This is the idea which we want to emphasize, scattered into unknown. The fifth model of my project is Tower of Hanoi, the architecture of algorithms. What it represents? Order emerging from strict rules, and it teaches us the concepts of recursion, exponential growth, and algorithmic thinking. It shows that even complex problems become solvable when we follow the right algorithm. If we moved 64 disks at a speed of 1 per second, it would take 585 billion years to finish. That is the power of exponent. This is Tower of Hanoi. This model represents exponential growth. Scientifically, it relates to algorithmic processes and optimization under constraints. Now we will solve this puzzle using these disks. The rule for this puzzle are, we can only move one disk at a time from these poles, and we cannot put the bigger disk on the smaller one. Let's start this. This model represents exponential growth, and scientifically it relates to algorithmic processes and optimization under constraints. Mathematically, the minimum number of steps required to solve the Tower of Hanoi is given by the formula 2 raised to power n minus 1, where n is the number of disks. Now let's put these disks in a random order. Now here we have solved this puzzle using a correct and proper algorithm. Even though this puzzle is considered very complex, still it teaches us that using a proper algorithm, which is in the form of repeated steps, we can solve this. By looking at my previous models, a question may arise in your minds. Is chaos helpless? The answer is no. Chaos can be managed and can be corrected using a proper number of steps, which is called algorithm. If we follow a proper algorithm, we can manage it and we can solve it. Even in this project, the thing is that we need to know a proper algorithm. This puzzle is an example of solvable chaotic problem. One wrong take can make it chaotic, and a proper algorithm makes it solvable. This is the taming of chaos, where we manage the chaos using algorithm. In real life, we can relate it with education. Just as our world is chaotic, by education, we give the students the path through which they can navigate this chaotic world. And this is what we want to convey. Even though life is a chaos, still we can get over it by a proper algorithm or a proper journey or a proper steps, which is algorithm in scientifically, and education if we talk in our life. Respected judges, the innovation of this project is not in the invention of these individual devices, but in their synthesis. I have created a physical syllabus that takes a student through the evolution of scientific thought. Dominoes teaches us linear causality, single pendulum teaches determinism, double pendulum teaches non-linearity and chaos. Probability board teaches statistical mechanics, and the Tower of Hanoi teaches algorithmic solutions. This project attempts to show that mathematics is not just about calculating answers for an exam. It is a language to model the behavior of the universe, from the orbit of planets to the flow of air. It has taught me that science is not about certainty, it is about understanding the boundaries of our knowledge. Thank you for your valuable time and for the opportunity to present this model.